So what's happening at the hole and what's happening at vertical asymptotes is happening at a specific value of x. So we call these localized behavior. We can look at horizontal asymptotes, and these are what we call endpoint behavior. So what is happening as x gets really, really big? What's happening on the right-hand edge, the left-hand edge as we go out to positive and negative infinity? So to analyze a horizontal asymptote or endpoint behavior, we can just look to see what's happening in the numerator and compare it to what's happening in the denominator. So I have a quadratic function in the numerator, and as x gets really, really big, this minus 2 really doesn't have much of an effect. As this x squared gets really, really big, this plus 2 has a very minimal effect on the value of x squared. And as x gets large, those two constant terms become insignificant. And what we can do is we can actually just kind of ignore them. So we can't ignore them to get an exact value, but it's approximately, when we have really big x's, like a million, this number and this number really are insignificant. So we kind of ignore those. And we then say the graph is going to behave approximately like 6x squared over x squared, which is really going to behave like 6. It's just going to start becoming closer and closer to the value of 6. And so formally we can write this as a limit. So limit as x goes to positive infinity. This expression, we do this simplification, and we end up essentially 6. Same with negative infinity. As x goes to negative infinity, same thing will happen. This x squared and this x squared is going to be infinity squared. Well, these two numbers don't really affect it, so we end up with the value of 6. So in this case, we're going to end up with a horizontal asymptote at a value of y equals 6. Okay, so this is going to have an asymptote along that line. So when the highest power is on the top and bottom, are the same on the top and bottom. We get a horizontal asymptote by just dividing the highest power coefficient. So what happens if the power is in the bottom is bigger? Well, that means then, if I use a limit notation, the limit as x goes to infinity, this is going to be, what's going to end up happening is the bottom is really, really big. The top just stays 5. Well, some number divided by really, really big number essentially goes to 0. So the limiting value is 0. It never actually gets there, so that's why it's a horizontal asymptote. It kind of goes towards 0. And so when I graph this equation, I'm going to have a vertical asymptote at negative 2. I have a restricted value there. And it's going to go down to infinity. It's going to go up to infinity this way. So it's just going to go down to 0. As x gets really, really big, it's going to go down to 0. And I can make the same arguments for if it's negative, goes to negative infinity, except the difference is this ratio will be negative because we're going to have a negative number in the denominator. And it's going to go to 0 from the negative side. Okay, and then we get a graph that looks like this. And just to highlight this, my horizontal asymptote is along this line y equals 0. So this one is where the highest powers are equivalent. Okay, so if the highest powers are equivalent, what that means is the rest of these terms here really are insignificant relative to the x squared term. And so we just ignore those, and we end up with something that looks like this. So limit as x approaches infinity of x squared plus 2x minus 3 over x squared plus 2x minus 3. This really just becomes a ratio of x squared over x squared, which is 1. And we can make the same argument will be made going to negative infinity, so we end up with a horizontal asymptote at y equals 1. Just draw that in. There's my horizontal asymptote. It's at y equals 1. That's going to match that value there. So if I factor this, I can get my factor terms. So it's going to be x plus 3, x minus 1. Here I'm going to end up with x minus 2, x minus 1. So these cancel out. So I end up with a hole. That's going to give me a hole. I've got a vertical asymptote at plus 2. X equals positive 2. And this graph is going to go up towards infinity. But then as it gets out to infinity, so my local behavior is a vertical asymptote at 2. At 1, I'm going to have a hole. So as it's a vertical asymptote here, and as we go to negative infinity, it's going to tend towards that positive 1 value. My horizontal asymptote, same here. As x goes to infinity, I'm going to go to positive 1. As x gets close to 0, it's going to go up to infinity on this side, down to infinity on this side. And my hole, maybe I should just kind of indicate that because this cancels, it's going to give us a hole at x equals 1. And at x equals 1, I think it's going to be equal to, let's see, at x equals 1, if I plug 1 in, I get 4 divided by 1, negative 1, it's going to be negative 4. So at x equals 1, y equals negative 4. So somewhere around here. Okay, so that coordinate is going to be my restriction, x equals 1, y equals negative 4. And I get that from just doing my limit. In fact, why don't we do that more formally, since we are using limits. Using my limits here, I'm going to do it like this. The limit as x approaches positive 1, as x approaches 1 of f of x, we end up getting rid of the divide by 0, plugging in 1, and we end up with a value of negative 4. And that's how I get that hole in that position. So at this point, we've only kind of really scratched the surface of this, and there's a lot of detail in here that may not make sense to you, and that's okay. The main ideas are this. The key features that we're going to focus on are vertical asymptotes and holes, and that comes from the denominator restrictions. So when we have divide by 0, with these two situations canceling, not canceling, we get vertical asymptotes or holes. Endpoint behavior is horizontal asymptote. So as x gets really, really big, what's happening to y? The y value approaches some value horizontally. If the powers are equal, we just take the ratio of those coefficients. If the bottom is bigger, it's just going to tend to 0. The other part is, so we have the key features, vertical asymptotes and holes, horizontal asymptotes, and the other thing that we kind of started to use is this idea of this formal notation of limits. Okay, and this is just, we're just introducing you to this notation because this is a notation that we use in calculus. So at this point we have a very vague and incomplete picture of the graph. So to get a better picture, we may want to make a table of values and plot some more coordinates to get a better idea of what's happening. But as we continue on, we're going to build on these pieces to start developing a better and better picture of what we're dealing with. And at some point, we would like to have a clearer idea based on, without drawing too many points, XY points on a table of values. It would be good. We want to try to get to a point where we can see what the behavior of that graph is going to look like without drawing too many points in a table of values.